Okay, so today our goal is to have a, I'm not sure if I can call it introduction, because I hope that in some way or form you already saw at least some of this material previously. So maybe more like expansion on a topic which here I described as second order systems. But I think more correctly it would be something like a oscillation theory for second order systems. In fact, subjects and disciplines in universities are different in different curricula, but one of the possible subjects that you could have in a technical university is oscillation theory, which would, among other things, specifically focus on how a system behaves under induced oscillations, what kind of oscillations it produces, and so on and so forth. A lot of it is a study of eigenvalues. So far for you, the main study of oscillations have been through Bode plots. So basically as a reaction, oscillations, that is a solution to a steady state solution to a ODE based on harmonic input. So input, which is a harmonic signal, right? Here we will, additionally to that, discuss the effects of eigenvalues, right? So eigenvalues are traditionally thought of as the stuff that influences how the system behaves in the transient process. And of course, they obviously influence steady state response as well. It is just that we care especially about transient process. You maybe are familiar with Lyapunov theory, which in linear case tells you that eigenvalues determine if the system is stable or unstable. If it is stable, means that transient process will dwindle down. That is, we do it by eigenvalue test, right? So it is easy to think of eigenvalues as, purely transient response kind of thing. Of course, they do influence steady state solution and everything else, right? Forced response. So today we'll see a little bit more of that. Right. And the reason we want to spend time on this in this course on mechatronics is because almost all of our systems will be either second order system directly or deal with second order systems. So let's just look into it for a second. So we will actually, we already saw, RL, RC, and RLC circuits, which is first and second order systems, right? DC motor, we already saw that it is a second order system in terms of angular velocity. We probably are familiar with spring mass damper. Spring mass damper is a second order system. All of those are linear systems too. They're not just second order, they're linear. And this is what I'm going to mean by second order in this lecture. Second order ODE, linear. This is, I think, that's what I mean. Right. Also, a lot of linearized models are second order. For example, linearized model of a pendulum is a second order model. As the linearized implies that it is linear, right? So this part is already kind of covered. And then the order of the model is usually the same between the linear model and a non-linear model. So any system which has a 1 degree of freedom, 1 mechanical degree of freedom, will produce a second order linearized model. So it'll be inverted pendulum, but also anything else which can be described as something with 1 degree of freedom. Right? So that is it. Now, why in mechatronics? Because our focus is on modules, right? Smaller components. Here we don't talk about robots, like how to build a robot arm. That is a much bigger task. We don't talk about how to control a robot arm. For that, you can go to Introduction to Robotics or maybe even to Fundamental of Robot Control, any of those courses. Here we focus on how to control modules, right? How to build a mechatronic module, like a motor, how to control motor, how to build this low-level kind of like subsystem. And those tend to be systems with 1 degree of freedom. Sometimes, like close to the end of the course, you would see modules with a few degrees of freedom. But it is quite typical for them to be 1 degree of freedom things. Okay. So for us, actually, the stuff we work with acts like a second order system. So understanding it, it kind of sounds, when you come from a background of doing pure math, n-dimensional systems each time, and so on. It sounds like going to specific dimensions when you get a lecture on specifically n equal to 2, right? You ask yourself, is it really worth it? Like, why not study n-dimensional systems each time, get abstract knowledge, and then apply it to any dimensionality? Well, this is, in general, a good way to think. But there are 2 reasons why it is, in this case, better to study second-order systems separately. One reason is because we have a lot of them in practice. So as I said, for us in Mechatronics, we deal directly with second-order systems. And they have their own peculiarities, which we can study. And while for general systems, it might be difficult to produce some of the results, some of the clear analysis, some of the exhaustive descriptions. For second-order systems, it would be easy enough. So we could exhaustively study them, right? So this is the reason, right? Because they exist and we can study them exhaustively without being bogged down by all the abstraction of n-dimensional systems. Okay, that is reason number 1. Reason number 2 is somehow it happens that a lot of dynamical systems naturally decompose into second and first order systems. This, and here I'm speaking very abstractly, so I apologize if, if this is too abstract or anything. But this happens because for the same reason as polynomials tend to decompose into second order and first order components, right? If you remember your polynomials, you remember that usually you can decompose them into products of second order polynomials and first order polynomials. For the same reason, you can decompose dynamical systems into combinations of first and second order systems. This would have to do something to do with, transfer functions having polynomials in the downstairs, like indeterminate. This would have something to do with eigenvalues being like solution to first or second order polynomials, right? Etc. etc. So there are various connections here. And if you understand very well first order systems and second order systems, this is a big step to understanding n-order systems, okay? So this is absolutely not a waste, even if outside of mechatronics, right? It is, in fact, I would say is a prerequisite knowledge for any kind of good understanding of control of dynamical systems. All right, so I hope I motivated you to pay attention to, this class, that it is not just like super specific, not interesting. Okay. Now let's just dive in. Double checks my microphone still works. 1 second, I will just do something. Can you hear me? Someone please tell me. Sometimes microphone switches.
Yeah, we can.
Okay, good. I think sorry about that. Okay. Now let's dive in. So we will start with a detailed discussion of eigenvalues. Okay, so we'll take a little bit of time and we'll try to be very thorough. Okay, so here is a second order system. I would say, homogeneous second order system. When I say homogeneous, I mean right-hand side is 0. So there are only, like, it is linear, but we agreed that we are going to discuss only linear systems. So there are coefficients in front of every term, right? And homogeneous means we don't have any terms with like t, for example. So the right-hand side is 0. Okay. We sometimes call this homogeneous part of the equation. All right. Now, we can tell if it is stable or not just by looking at it. For example, if this is bigger than 0, if this is bigger than 0, and this is bigger than 0, then it has to be stable. Like this whole thing would have to be stable. Why is it so? Why is it so? Because this is equation that describes mass spring damper system. Okay, and so it describes the actual, physical entity. The mass for mass spring damper is obviously positive, same as mass for any physical system is positive. The coefficient of viscous friction is positive, and spring stiffness is positive. That is, for physical system like that, those three are always positive, right? And naturally, energy leaves the system. So the system with the friction, and here this term would specifically be viscous friction, linear viscous friction. It eats away at the energy of the system. So as system moves, the total energy of the system diminishes. So it means that total energy as it diminishes towards 0. So it, of course, total energy contains mechanical and, kinetic and potential energy. Kinetic energy depends on velocity, potential energy depends on position, in this case, on deformation of the spring. But both, like the sum diminishes to 0. That means kinetic energy also diminishes to 0. Means motion will be slowing down. So there'll be less and less of motion. Eventually, the system will stop. So this is a kind of definition of stability. That is a physical way of looking at it. You can write down Lyapunov function for it and prove stability through Lyapunov function. It wouldn't be too difficult. You can also just count eigenvalues of the system. You'll find that they will be negative. Okay. Now, it is important to keep this test in mind because for second-order systems, it is extremely useful. And we are discussing second-order systems today. So it's, like, again, sounds like a trick which you would hardly use ever. But it's like inside this area of second-order systems, it is a very useful trick because computing eigenvalues takes time. And looking at the science doesn't take any time. Okay, right. Now, this sounds oddly specific, right? It doesn't, it is only telling you if it is stable, if this condition is true. It doesn't tell you if it is unstable or if it is false. In fact, you cannot judge simply from this fact, for this test, if it is unstable. But what you can do is, let's say you have a system where M is negative, okay? If M is negative. Well, then you can multiply everything by -1, and M will be positive, okay? So let's say you have equation is negative first, like higher order coefficient is negative, okay? Coefficient in front of y double dot. Multiply everything by -1, you get the first coefficient positive. So the first condition here is always satisfied. Like if you massage your equation into correct form, first coefficient is always satisfied. So it's not really a condition that you need to check as much as it is a condition that you need to acquire before checking. Okay. And then after you acquire this condition, first coefficient is positive, those two become necessary and sufficient conditions. Yeah. So if, in particular, if like this is positive, it basically means that the faster you go, the more you accelerate, right? So it's like if you think about it, that would be the kind of force which looks into the direction in which you are going and gives you even more speed in this same direction. So the work that this force will produce would be positive. It will kind of like increase the energy of the system. Same here. Yeah. So, yeah. is sufficient to say, usually in practice, it is sufficient to test the condition for, since usually what you want to do is to just verify that your system is stable, okay? It is quite rare to use this condition to verify that the system is unstable, okay? So if you see that this condition is met and the system is stable, you can be absolutely certain everything is fine. If you see this condition and it is not verified, like something is not bigger than 0, right? I think the basic sanity will tell you, okay, now I have to compute eigenvalues. So while I like this test, I definitely don't see someone using it to prove instability of the system and just walking away. Like in a practical situation, a situation which you care about, after you look at this test, you would, and it fails, you would compute eigenvalues and do a proper testing. But usually it is just meant to calm yourself down when you see the second order system, to just make sure, okay, it's supposed to be stable, it is stable. Okay, so this is just some stuff to make you faster at evaluating the systems. Remember, again, you can make mistakes, so double check everything, and this is one of the way you can double check, right? Eigenvalues and this method, for example. Okay. More principled approach now. More principled approach is to, of course, compute eigenvalues. Let's start by dividing everything by m. You can notice this is equivalent to making sure that the m, the first coefficient is bigger than 0, because once you divide everything by m, you would get a 1 in front of the highest order derivative. So we start by doing the same thing in both cases. It is just that here it is more radical. We divide everything by m. So we get new coefficients, 1 here, mu here, and c here, where mu is 0 divided by m. So it is this guy divided by this guy. Okay. And c here is c0 divided by m. So this guy divided by this guy. All right. Now we have second order system, which doesn't have any, it has a 1 in front of higher order derivative, so only has 2 coefficients. And this kind of makes sense, because if you multiply this whole system by any number, all 3 coefficients will change, but the behavior of the system will not change, because you didn't do anything to the equation. You just simply multiply everything by some number. So you scaled all the coefficients, but the relations between them did not change. So in fact, even this description here only had 2 parameters. It is just a void distributed in the form of 3 parameters. But the only thing that mattered even here was this ratio. Like those ratios mattered, but not the particular values of individual coefficients. This is a better description of the system. So if you work with the system, it is better to use something like this than something like this. Okay. Now, we could transfer it to state space form because we want eigenvalue analysis. So eigenvalues go well with state space. So we transfer to state space form. How do we do it? Let's say x1 is equal to y, x2 is equal to y dot. So y is here, y dot is here, right? So that's what we have. Okay. Right. And remember, we could always say that x1 dot equals to x2, right? x1 dot is q dot, x2 is q dot, so x1 dot is equal to x2. Okay, so let's look at this equation. x1 dot is indeed equal to x2 by multiplication. You can see how it works. Like 0 times x1 plus 1 times x2. Okay. Now x2 dot is equal to x1 times c with a minus sign, which is, this component, plus x2 times mu with a minus sign, which is this component. That's it. And x2 dot itself is y double dot, of course. So we just transferred everything to the right-hand side. We got this. Right, so I'm not going to belabor this too much because I expect you have already seen this. So it's, yeah. If there is any problems with, you have already seen this even in this course with the motor, but like if you feel any trouble with this type of manipulations, you can write me in the chat or private message, and I would send you like suggestions for reading. It is it's quite common transformation, like to state space. Okay. Now let's consider this linear system that we just created. This is a linear system. So we can find its eigenvalues. How do we find eigenvalues? Well, there is a formula for eigenvalues, which same as previous ones that was based on analyzing that as a physical system. This one is just nice, and it is nice to remember because eigenvalues by themselves, computing them, I think it's a little bit of a chore. I'm not sure if any of you like to do it by hand. I have a suspicion that you don't. I have a suspicion that almost every one of you computes eigenvalues on the computer. So university sometimes tries to push you to do it by hand. Okay, but for 2x2 system, computing them by hand is not a chore. It's still a little bit of work, but it's not such a big deal, And it is again the reason why you need to study 2x2 systems, because for them you can actually do those kind of things with less effort, and it's like when something can be easily done, it often gives you opportunities to do more thorough analysis, etc. So here, eigenvalues are not difficult. Let's look at them. So the eigenvalues are computed by this formula, where T is trace and D is determinant. So what is trace? Trace is elements of the diagonal summed. So it is of the matrix. So it is 0 plus minus mu. So trace is minus mu. Okay. So you can see already it's quite simple, right? And the determinant, you remember what determinant is? It would be this element times this element minus this element times this element. Well, the first two, the product is 0 because one of them is 0. And the second one, the product is minus c. So we have 0 minus c is plus c. So that's what we have. Okay, so trace and determinant, as you can see, it's again quite simple. And if you do it often enough, you would find that you could even memorize that trace is just minus mu, determinant is just c, and you could substitute them into this formula. So it depends on what you use those for. But I think in general, memorizing this formula might be best because 2x2 systems are more general, I guess, than just homogeneous equations that we looked at today. Okay. So more, I guess, like not more generous, but it is useful to be able to compute eigenvalues for any matrix, not only for this type of matrix. Okay, so let's look at the formula. So after we substitute, we would get here, let me just go stage by stage. So instead of t, trace, we will get minus mu, right? Instead of t squared, we would get mu squared, right? Instead of d here, we get c. And that is it, right? Quite simple. So minus mu plus or minus mu squared minus 4c divided by 2. That is eigenvalues of the system. So somehow eigenvalues of our system depend on the viscosity. Remember, viscosity divided by mass. So it is always normalized by mass. So this is viscosity divided by mass. There's a minus sign, plus or minus this entity, which has a viscosity squared minus 4c. Okay. Yeah. If you remember how you solved second order equations, you may recognize it pretty well, like this this part here. Pretty sure it had a name. All right. So you would have this whole thing, which is recognizable from your high school, in at least in form. Okay. Okay. Now let us analyze what we got with this formula. So first, let us see what happens when both of those are positive. Remember, we said that if they're positive, the system have to be stable. Okay, so this is just simply comes from understanding how physical like system that is analog to this mathematical one behaves. So now let us concretely see what happens. So we can recognize two different scenarios. One is when this value under the root is also positive. Well, what does it mean for it to be positive? Well, what it means is that this square is bigger than 4c. Okay, so it is not sufficient for those two to just be positive. For this scenario specifically, we ask for mu squared to be bigger than 4c. Okay. Okay. So, all right, that is fine. Since the whole thing is positive, we can see that, like, when we subtract from m squared 4c, okay, since c is also positive, right? This whole value under the root will be less than mu squared. Okay, I apologize. It sounds completely obvious, but of course it isn't, because if c was negative, I couldn't say that, right? So I'm only able to say it because c is positive. All right. So let me repeat myself. Mu squared minus 4c will be less than mu squared because c is positive. Okay, and the whole thing is positive too because that's our condition. Okay, so this whole guy is less than mu, like the value under the root is less than mu squared, but the value after you take the square root is less than mu. Okay, so this is the situation. So this is less than mu. So if you look here, what we recognize is that it is plus or minus value that is less than mu plus negative mu. Okay. So this is a negative value equal to mu. This is a positive or negative value, which is less by magnitude than mu. So if both of them are negative, then we get just a bigger negative number. Okay. If this guy, like this green guy here, is positive, we still get a negative number because by absolute value, this number is less than mu. So minus mu overpowers it each time. That is why we get purely real and negative eigenvalues. Now, the fact that they will be negative, the real part will be negative, was clear from the beginning because we remember this was our condition. So it's no surprise that they're negative real eigenvalues. What is surprising is that they are purely real. This is not coming from previous analysis, like this trick with analog to physical system. This comes from understanding the expression for eigenvalues. Okay. So in this case, it means no imaginary part. And the condition, again, is that this guy is positive. All right. And you can see it is, now that we shoot all of this, I think it becomes obvious. Now, let me say why it is obvious. Well, we know that this guy would have negative real parts of the solution. We know it with this condition. Okay, with this condition, we know it is going to have a negative real parts. So this part we already know. Now, would it have imaginary parts? Well, if this guy is positive, it means square root of a positive number is a positive number, plus or minus, doesn't matter. So imaginary numbers don't spring out of something like this. So it has to be negative for imaginary numbers to appear. So obvious. The fact that it is purely real, obvious, because this guy does not have a chance to produce imaginary numbers, and negative real. Negative because of the test that we saw previously. So it's while it is required some look in the math, once we understand what's going on, I think we don't have to memorize it. It's quite easy to just get from understanding. Okay, next one. Let's say this guy is negative. Okay, let's say this guy is negative. By the way, this could have been 0 too. Everything that I said would have been the same if it was 0. Okay. Now, okay, go back. Negative one. The mu squared minus 4c is negative. This, of course, means that 4c is bigger than mu squared. Okay, since c is still positive number. So mu squared minus 4c is a negative number. Well, in this case, this guy is a purely imaginary number because square root of a negative number is an imaginary number. Okay. It is easy, since you already saw quite a bit of imaginary numbers in various contexts, it is easy to forget some of those things, right? Let's keep it in mind. Square root of a negative number is imaginary number. It doesn't have a real component, okay? Like those simple things, once you get through a lot of use for imaginary numbers, it's sometimes slipping out. So this is a purely imaginary number. So the eigenvalues in this case are complex with negative real parts. How do I know that the negative real parts are there? Well, because this is a negative real part. Negative real part is minus mu. That's all. Divided by 2, basically. Don't forget this. So a negative real part, real part, in this case, is mu divided by 2 with a minus sign. And mu, remember, is a positive number. Okay, so you see what happens if this, let me go like this. If this guy is positive or 0, we have negative and purely real eigenvalues. If this guy is negative, we get negative real part of the eigenvalues plus or minus imaginary part. That's it. Now, if you notice, there is a bigger or equal to 0 here. So if mu was equal to 0 and this guy was negative, then we would have purely complex eigenvalues with 0 real part. This, if you remember Lyapunov theory, what means marginally stable system. Okay. All right. So this, I think, we exhaustively looked into. Pause me at any time and ask questions. I would be happy to answer. Okay. Now, if mu is still positive, but let's say c is equal to 0. So c is equal to 0 means that we have like here we have a simpler expression. Okay, then you can notice stuff becomes a little bit obvious. So in fact, this guy here is a plus or minus mu, right? Plus or minus mu, because mu squared is always positive. Square root of a positive number is a positive number, cannot be imaginary, right? And we have minus mu, plus or minus mu. Okay, so minus mu plus mu is 0. So this is one eigenvalue. And minus mu minus mu is minus 2 mu, but divided by 2, it is just minus mu. So second eigenvalue is minus mu. So now we have one eigenvalue is negative, is purely a real number. Second one is 0, just 0. So the system is then marginally stable. And here I will just take a second to explain what it means physically. What it means physically is that the system will be happily dissipate velocity until the energy goes to 0. So this is what this eigenvalue means. System will happily dissipate energy until the energy is no longer. So kinetic energy will go to 0 eventually. The system has no potential energy because C is 0. So the system does not have some source of potential energy which would somehow store some energy in coordinate. Okay. And what will happen is as the system dissipates its energy, it will find some steady state solution. Okay. So eventually velocity will tend to 0 and it will find some steady state solution. Okay. It will approach some steady state solution. I mean, when I say approach some steady state solution, what I mean is just like it will not kind of like go all over the place continuously. This velocity will dwindle. Okay. But which place it will approach depends on the initial conditions. Like there is no preferred state in terms of position which it would like to approach. For a normal system with positive C, it would prefer to approach state y equals 0 because that's where potential energy is 0. For this case, it doesn't have a preferred state, so it will just approach somewhere. Okay, and this is what it means to be marginally stable. So instead of approaching 0 asymptotically, you approach something. Okay, just not 0. You approach something. And we say by definition marginal stability means that as time goes to infinity, our error does not grow beyond some boundary. So we could always find some boundary and say it's not going to grow above this boundary. So marginally stable. All right. So that is a complete analysis for this case, for the case of positive coefficients. Good. Good. Let's move on to the next stage. Now, let us consider a situation where mu is positive and C is negative. So this is the one which I remember when I was talking at the beginning, I did not feel comfortable telling you the answer. So let's, now we will be able to see the answer. It's like I don't have it in my memory. I don't have it in like memorized. So yeah, it's nicer for those cases to look at the mathematics of eigenvalues directly. All right. So again, mu is positive, C is negative. Well, since mu is positive, this guy here is, mu, even if it was negative, it wouldn't make any difference. This guy is always mu squared, positive number. Okay. This guy here is also a positive number because C is negative. Okay. So C is negative, but there is a minus sign. So this totally, this is like a positive number. So it will be positive number plus positive number. So obviously the sum of those two numbers. So again, let me show. The sum of these two numbers will be bigger than only mu squared. Okay, the sum will be bigger than mu squared because we add positive numbers. And that means that the square root of the whole thing will be bigger than mu. Okay, square root of mu squared is mu. Square root of a bigger number is a bigger number. Square root is a monotonic function. Right? Plug in bigger number, you get a bigger reply. Okay. For numbers bigger than one, I add. So I'm afraid to say something stupid. So unfortunately, always try to limit what I'm saying. So okay, we have this function here, and we know that this guy will be bigger than mu. All right. Let's remember the how eigenvalue looks. So I should have kept on the slide. Let's look here. So this guy is bigger than mu. You said, right? It is bigger than mu. Here we have minus mu. And this guy is plus or minus bigger than mu, right? So number bigger than mu is a plus or minus. If it is a minus, we get a big negative number. So everything is fine. Minus mu minus big positive number. So totally big negative number. If it is a plus, so we have minus mu plus big positive number. Big as in bigger than mu. So the answer is positive, right? So we have mixed eigenvalues. That's a reply. So the eigenvalues are purely real. One of them is positive. Purely real because this guy is obviously purely real, like positive number, square root is a positive number, not imaginary. Okay, so the system is unstable. So you see this scenario, which I wasn't comfortable talking about off the top of my head, is actually, yeah, it is unstable. And we can prove it by this simple argument. Okay. And if you ever encounter this situation in your practice, you'll probably either compute it by MATLAB or Python, or just do the same analysis that I did here. And this won't be a waste, right? So every time you encounter something unusual, much better to double, triple check. Okay, and of course, this type of situation is for mechanical systems completely unusual. For control systems, less so, right? But yeah. Okay. Now consider another scenario. Mu is less than 0 and C is less than 0. Okay. So mu is less than 0, C is less than 0. Okay, so both of them are negative. Well, this situation here remains exactly the same because mu is being squared. So if mu is less than 0, it is still like this square root is still bigger than mu. Okay, so this square root is still bigger than mu. Okay, so the sign of this flip of sign did not change this fact. Now let's go back one slide. What we see is again plus or minus big number, but now this guy is positive. Okay, this guy is positive now because we flipped sign. So what happens is we have a positive number minus a bigger negative number. So one of the eigenvalues will be negative. Now, positive number plus a bigger positive number. Well, the second value is positive. So we have positive and negative eigenvalue. So at least one of the eigenvalues is still positive. So we have the unstable system. So both of those cases, this case and this case, provides us unstable systems. Good. That is, notice these cases are characterized together by negative stiffness coefficient. So negative coefficient in front of y, which is like zero derivative. So like there is y double dot, y dot, and y. So this is the coefficient in front of y divided by mass. Okay. Now let's consider this case. Mu is negative. Mu is negative. So this is the one where I was confident. Maybe I will prove myself wrong right now. So it would be fun. Yeah, and I was confident. Remember that it was unstable. So we'll see during the analysis now if I was correct or not. And C is positive. So again, there are two scenarios. One scenario is mu squared minus 4c is bigger than 0. Okay, so this guy could be negative, positive, right? Let's assume it is positive. If it is positive, remember we already looked into this. If it is positive, it has to be less than mu. Why again? Because C is positive. Okay, so this holds because C is positive. Like positive C means that this positive number here would be lessened by subtraction from it another positive number. Okay, and this works because this whole thing is positive. Okay, all right. So this guy is bigger than mu, and now I think we can just by memory go say that minus mu plus or minus smaller number would always give us sorry. I went too fast. I guess let us be more slow. Mu is negative. Okay, so remember mu is negative. So it's very easy to forget those details. If mu is negative, so it is negative with a minus sign here. So positive number together it is a positive number. Positive number plus or minus smaller positive number would always give you a positive number. Okay? So positive number minus a small positive number is still positive. Positive number is plus a small positive number is a bigger positive number. Okay, so both are positive. So that is even worse than before. So now both eigenvalues are real and positive. So unstable, no operations. Okay, good. Now this guy could be less than 0. What happens if it is less than 0? Well, then this guy is purely imaginary. Purely imaginary. And remember, mu is less than 0, and it is multiplied by minus 1. So the real part is minus mu divided by 2. Mu is less than 0, so the real part is a positive number. So it is positive with a complex part. Like, eigenvalue is complex with positive real part. Unstable again. So here's our answer. All right. In this case, we got mixed eigenvalues. At least one of them was positive. In this case, we get eigenvalues which are both of them are positive. Okay. So all of this is unstable. Here's so intuition worked, I guess. What I presented in the beginning of the lecture worked. Yeah. This is a condition for unstable system. This is a condition for unstable system. Okay, but we required this analysis to prove to ourselves because Okay, and here is now final result that I present to you at the beginning. If they are those two guys are positive, the system is stable. If one of them is negative, the system is unstable. Any questions so far? Okay, let's go on. Now, let us go back to this equation. we can write a characteristic equation for this ODE. The characteristic equation is basically one of the many tricks that people use in differential equations theory. That is basically replacing like u double dot with y double dot with k squared y. Mu dot would be, oh sorry, it will be here. Let me just double check what I did here. Yeah, okay, everything correct. So this will be replaced by k squared y, right? This will be, yes, mu k, and this would be c, yes. So basically you can think of it as a differential operator, I guess. If you remember how we produced, yeah, like, you know, characteristic equation is looks a little bit strange when you look at it. But if you remember Laplace, how we did work with Laplace, it is almost exactly the same. We got like, in Laplace, we would have had like p squared times y plus mu p times y plus c times y. Then we get rid of y, basically by, we usually would have like u here, and we say, what happens if we write like y divided by mu, or u divided by y, and we get a transfer function. And this would be like a denominator of a transfer function. Okay, so this is something that makes kind of more sense to me. But also, characteristic polynomials, there are other ways to get it, like through a characteristic polynomial of a state space system, so of a matrix, and so on. Okay, so anyway, characteristic polynomial, this is it. K, you can think of like power of k is related to derivative order, right? So second power, first power, zero power. Okay. All right. I understand why I feel like there is a mistake. There is a mistake, of course. Like there is no y here. I was looking at it for like 4 minutes. I was trying to understand why do I feel so uncomfortable. It is k squared plus mu k plus, you know, now I feel comfortable. Okay, sorry about that. So that was a typo. All right, now we can find the roots of it. This is now just a second order polynomial. And the roots would look like this. Okay, so if we find roots of this polynomial, the roots would look like this. And what is interesting is that this is exactly the same formula as we saw before. So the roots for this characteristic polynomial eigenvalues, apparently. So it is very similar to determinant race formula. So if you feel more comfortable working with this kind of stuff, like going from here to here, right? And then remembering exact formula for roots of a second order polynomial, then this root is quite clean, and you don't have to worry about determinant or anything like that. I think this root is maybe better when you don't work with state space, because transferring to state space only to find eigenvalues is maybe overkill. So remembering this route just for eigenvalues, I think is maybe worth it. Okay. All right. Now let us consider transfer function. So transfer function, as I said, it would have been the same, the process would have been the same as doing this here, right? One element here. So it would be, basically it would be, if we try to make a transfer function for this equation, we would have had s squared y plus mu s y plus c y equal to u. This would be our, our equation. Okay, in Laplace form. Then we would have taking y out of the brackets, in this fashion. In the next stage, we would have said, all right, let us find what is y divided by u, right? So the, I guess, ratio of those two guys. And this will be 1 over this whole bracket. So this is what we would have done. This might look, let me just double check. Okay, that was mu. All right, so this might look a little bit suspicious in terms of what is this ratio. So if it looks suspicious, I invite you to get any lecture on Laplace transform. I have a lecture, so you know, so just refresh it. But again, we had it already in this course. This relates to the fact that the way you use transfer function is you take y and you say it is a transfer function times u. So y is a transfer function times u. So you take input multiplied by a transfer function, you get output. Output in this case is y, input in this case is u. Okay, so this is the idea. Okay, now the transfer function for the system would look, as I said, like this. Okay. This is a transfer function. C here is a Laplace variable. So it is essentially it is a complex variable with a real and imaginary part. Now, poles of transfer functions are solutions of the polynomial in its determinator, right? So poles of the transfer function are solutions to this guy. And you already see where we're going. This is the same as a solution of characteristic polynomial, right? Which is the same as eigenvalues of the linear system, okay? So those three things, solutions to characteristic polynomial of the ODE, eigenvalues of the state space representation of the ODE, and poles of the transfer function of this ODE, they're one and the same. So just same mathematically, the formulas for them would be exactly the same. So they are the same, right? This type of observations, I think, are suspiciously easy to make. It's just my personal philosophy, so please take it as you like. Those are suspiciously easy to make. So when someone says, okay, poles exactly the same as eigenvalues, exactly the same as characteristic polynomial. So when you make such easy statements that kind of connect wildly different things, my reaction is, let's check. And in order to check, you need to know how to check. So you need to remember how to transform this into Laplace and get this, right? You need to remember how to do characteristic polynomial, and you also need to remember the formula for exact solutions of second order polynomial. And finally, you have to remember how to do this state space transformation and something like this, like eigenvalue formula. Okay. If you remember all of those, you can check and find that indeed they look exactly the same, right? Okay. So I don't want to kind of like teach you to feel confident in those strange truths that people tell you, like those two things are completely the same. So, no need to compute this when you can compute that. Instead, what I want to teach you is that there are those connections and they're extremely useful, but you have to double and triple check yourself to avoid falling into traps. And especially because when you double and triple check, you understand it better and better. So it's like not a wasted effort. All right. Any questions about all of this section? Basically, we are done with like big part of the lecture. We will now go to like second part of the lecture. So if you have questions, ask now. Yes, no questions. So I'll go on because I think we are also running out of time a little bit. Just, maybe someone can tell me how much time do we have?
20 minutes.
20 minutes, okay. Well, I think I should be, maybe not. We'll see. We'll see if I manage. All right. Let's go on. So another way to write the same equation is by writing it in the what we call a natural frequency representation, right? So this at this point, I'm pretty sure this is new material for you. Like previous one was probably maybe like you saw it somewhere. This should be new. All right, natural frequency representation. This is basically means introducing new variable. So zeta and omega n, right? And we write it like this: y double dot plus 2z zeta omega n y dot plus omega n squared y equal to 0. So this is what we write it as, where omega n is a natural frequency and zeta is a damping factor. That is names for those variables, right? So this quantity that you can see, let me use it. This quantity here, zeta times omega, is called damping attenuation. Attenuation is basically means like dwindling, like how much you dwindle something. So it's damping attenuation. Those two parameters, okay? So omega and zeta are related to our old parameters mu and c as, so they're related as omega is equal to square root of c and zeta is equal to mu divided by 2 square root of c. But now this may sound wild, like why such a specific stuff? But it is not wild. So let us just double check and we will see that everything is correct. So if we square this, so square root of c we multiply with itself, like here, we get c, which is exactly should be what should be in front of y, right? Like old equation, remember, was y double dot plus mu y dot plus cy. So this guy square get us c here, correct. Okay. Now what we get here is more complicated. Like first we have 2, then times divided by 2, so this cancels. Then we get mu divided by c squared times c squared. So c squared cancels, square rooted. So we have again 2 times mu divided by 2 divided by square root of 2, c times c. So 2 cancels, square root of 2 of c cancels. So in the end, the only thing that remains is mu, which is exactly what should be here. So this whole guy is mu. Okay, that is it. That's it. With that, the expression for eigenvalues becomes this. Okay, so I'm not going to derive it for you. You can just substitute, substitute this into substitute this into the previous equations, or derive it directly for this equation. Like there are many ways to do it, but this is the result. This is the result. So you can see what is interesting is we have this natural frequency in front of our square root now. And here we have this damping attenuation. So this product of natural frequency and damping factor. Right. Under the square root though, what is also interesting we only have damping factor. So natural frequency does not appear under square root. So this is a little bit nicer because previously, I remember we had to always consider two cases, like what happens with relations between mu and c. Like we always had to consider this. Now we don't have to consider it because under the square root, there is only one variable. And what is especially interesting, under the square root, what happens depends entirely on the size of z, zeta, on the size of zeta. So it's like whether or not it is bigger than one, basically, it would decide what the situation would be. Like it would be imaginary numbers, or it would be positive real number. Yeah. Right. Yeah, and it cannot possibly be a positive number, right? So it cannot. Yeah. Okay. So it's can be imaginary number or positive real number. All right. Let's go on. Now, with this representation, what we have is basically two scenarios. One scenario is the system can be overdamped. So have pure real negative eigenvalues if zeta is bigger than 1. Critically damped if zeta is equal to 1. And underdamped if zeta is between 0 and 1. So let's go back and understand what this is. So if z is bigger than 1, this whole thing is a positive real value, positive real number. All right, positive real number. There is plus or minus sign here. Okay, but notice the value for natural frequency appears in front of both of those guys. So essentially, it's like a common factor. We can factor it out. So like we can put it out of the brackets. And in the brackets, it will be minus this number, plus or minus the same number, but made smaller by 1. So it will be for bigger zeta, it should be they should be negative. Let me see. Pure negative eigenvalues when zeta is bigger than 1. We assume positive frequencies, by the way. Like those frequencies, we assume that they are positive. All right. Good. If zeta is equal to 1, what happens is this whole thing becomes 0, right? This whole thing becomes 0. So this is the situation. This is 0. So all of this goes away, and here it is 1. So lambda is equal to just minus omega. So when it is critically damped, eigenvalue is minus omega. Okay, nice to know. Why it is called critically damped? Well, if zeta becomes any smaller, what happens is, so it got smaller, this whole thing starts to oscillate. So this whole thing becomes a purely imaginary number. Since this is less than 1, so this value under the square root is negative. So this square root is itself becomes an imaginary number. And we have negative guy here. Remember, we still assume that the damping factor is positive, just between 0 and 1. And it is negative number, plus or minus imaginary number. So the critically damped, the part where we said critically damped, refer to the fact that if you change it a little bit, it goes into oscillations. So critically damped means basically the eigenvalue such that you perturb it a little bit and oscillations can start. Usually it means that this guy is equal to 0. Because like if this becomes negative, oscillations will start. So 0 is critically damped. Zero value under this root. All right. So you can see why this representation is so nice, because it is very easy to memorize. Like previous one was kind of complicated. No one was going to memorize anything there. This one is very easy to memorize. Bigger than 1, okay. Stable through negative eigenvalues. 1, okay, stable but critically damped. This guy is stable but with oscillations. Okay, so very simple. All right. So the system with would have purely imaginary eigenvalues if and only if this guy is equal to 0. So that if that is equal to 0. Yeah. All right. Let's look at this. Just for a second. So if this guy is equal to 0, like what it means is that this guy is also equal to 0, right? So if z is equal to 0, this guy doesn't exist. So we don't have a real part. And that is the only way to make sure that the real part is 0. Here it would be 0. So we'd have square root of -1 is I. So the imaginary number, the imaginary is the eigenvalues would be plus or minus omega times I. So this is the only solution is purely imaginary eigenvalues. Purely imaginary eigenvalues means that there is no like positive or negative real part. So the solution is not going to grow or decay. It's going to stay oscillating. Okay, if you remember how eigenvalues affect the solution, it's not going to decay, not going to grow, going to be just constant oscillations. Okay. Now, why do I say that it has to be this guy, that like zeta, that has to be 0? Why not omega? Well, if omega is 0, the eigenvalue is just 0. Like there is imaginary part is 0, the real part is 0. So this corresponds to the situation where there's no oscillations, there is no decay, there's nothing. Okay, it's like a trivial solution. And if you look at how it would look like if both of them, if like this guy is 0 and this guy is 0, what it means is that the equation looks like q double dot is 0 is equal to 0. This is not a very interesting system. All right. So need to be careful about the cases. This is a very specific case. All right. So this is a requirement for purely imaginary eigenvalues. We'll see why it is important in a second. All right. Now there is a tool for discussing this, which is I guess we call it like diagram, like pole diagram for natural frequency representation. Looks like this. And what does it say? Well, it say that here there are axes that determine real and imaginary value of the poles, so eigenvalues. Okay. Now, here we have a polar representation of the same poles. So here's a pole, and it has a polar representation. Polar representation is angle and length. Okay, so the length of the vector and the angle of the vector. Okay, amplitude angle, you could say, if you want. So this is the amplitude or length, and it is equal to natural frequency. Right? Good. And this angle is equal to inverse cosine of this damping factor. And this is nice. Why? Well, because you could see that as this damping factor approaches zero as we go here. This approaches zero. So this would be inverse cosine of zero is, correct me if I'm wrong, should be 90 degrees, right? Yeah, 90 degrees. So as it approaches zero, we go here, which, as you can see, is imaginary axis. Okay, this is imaginary axis. So we lose our real part of our pole. And this is kind of interesting because like we retain the same natural frequency. So we say, okay, let's leave natural frequency alone. We only care about damping factor. And we can see what happens when we move it around. As on the other hand, we move it around, let's say, in a different direction. We approach, let's say, 1, the number 1. Here is damping factor equals to 1. What happens is our 1 is, of course, inverse cosine of 0, right? So the angle is 0, right? What happens is our imaginary part of our poles goes to 0, right? So it becomes purely real, okay? Purely real. That is what we were talking about, I guess, with critically damped. All right, so this diagram is nice, and you can look at it. I think, it's just like one of the ways to make it make sense, but you don't have to. It's quite clear even without diagram. But it's very nice to look at, I think. Okay. Right. And by the way, if you want to look at this, what I would recommend to you is to think what happens when damping factor becomes greater than 1. Okay, like where it will be in the diagram and so on. Okay. Now, let's consider the case with purely imaginary poles. Well, I will go for 8 more minutes and then I will stop. Like I have 8 more minutes, right? I think. Correct me if I'm wrong. If I'm delusional, if I
yes.
No, I have 8 more minutes, right? Okay, good.
You have.
Great.
7 more.
Okay. Thank you. So purely imaginary numbers, poles. That is interesting topic because it has to do with a critically important part of building any system of this type. Right? So let's look into it very quickly. So let's say the damping factor is equal to 0, which by the way implies that mu is equal to 0. Why does it imply that? Well, let's quickly go back and see that damping factor is mu divided by 2c. So c like would not be infinite, right? And the only way for this number to be 0 is for the numerator to be 0, right? Determinant is not this part of the ratio is not going to be going to infinity, so this has to be 0 for this to be 0. Okay, good. So what we have is this guy being 0, and then this implies purely imaginary poles, as we were talking before, right? And those purely imaginary poles are lambda equals to plus or minus I omega n. So we have in my eigenvalues, which are plus or minus I omega n. So natural frequency. Good. Not only that, but we can also write how the differential equation looks like. It looks like this. Why? Well, because let's look at the differential equation. We cancel this term because it contains 0, right? So 2 times 0 times something, it's just 0. So we only have those two left, this and this. Okay. Now we can propose a solution of this form. Y is equal to A sine omega t plus phi. Right? I just propose that this is the solution. Okay. If I differentiate this guy once, what I get is this omega t will get outside. Right? A would stay the same, so A would not change. The value under the trig function will stay the same, but sine will become a cosine. Okay, sine will become a cosine. Okay. Second derivative would be quite the same, so we will get another omega out of the brackets, right? Like this omega will get out one more time. This omega. A will stay the same. The expression under the trig function will stay the same, but cosine will become minus sine. So it will just minus sine from this cosine. Okay. Now what I do is I substitute this guy into here, and I substitute this guy into here. And this is what I get. Well, let's see. So this is the guy I substituted instead of y. And this is the guy I substituted instead of y double dot. And you can see that they cancel each other. Like after I substitute, this becomes equality. So this equation became equality. And it is like same expression with minus sign here, plus sign here. So is equality, so it means that it was a solution. What I proposed was indeed a particular solution to this equation. Okay? Well, this is what we call particular solution, right? Like solution that you can substitute and it solves. Okay? It's a particular solution. Yeah. If for this particular right-hand side, which is in this case happens to be 0, right? Often, or usually we find particular solutions for more interesting right-hand sides, but this works too. Okay. Good. Now, what we saw on the previous slide is that this system will oscillate, like the solution of the system is basically a oscillatory behavior. It will oscillate, like the solution will oscillate with frequency Fn. So let's just look at it before. Notice that solutions that I proposed contained omega n here. So there's a sine omega n times t plus f. So there's an oscillation, but the frequency of this oscillation, angular frequency, right, is this omega n, right? So this is what is this? So this is what's going to happen. It's going to oscillate with the frequency omega n. This is why we call it natural frequency. This is the frequency with which system will oscillate if no damping is applied. So this is now critical. I understand we have like 2 minutes of lecture, but this is critical. So let's try to anyway remember it. If we don't have damping, no friction to sap the energy out of the system, what we'll obtain is a solution. The system will oscillate with a certain frequency under no external oscillation. So notice there is no external like something that drives these oscillations. System will oscillate on its own just from initial conditions. So the energy that is in the system will produce the oscillations. So the system will just go up and down without any help from outside. And this is called natural frequency. That's why it is natural, because it is natural to the system. It is not driven by outside sources. Okay. Now it shows that if we pass a harmonic system with an actual frequency Fn through this transfer function, we get 0 output. Okay. So what is this transfer function? Well, this transfer function I got it by just find the transfer function for this system, and essentially it is a transfer function from u to y. Okay, from u to y. This maybe it requires a little bit more explanation, but basically, if we I'm not sure if I want to like just go this fast through, But remember how do we do Bode analysis on transfer functions? We say we replace S with I don't know, IXC, like with the I and the frequency variable. And this frequency variable is the frequency that we analyze. Let's put instead of frequency variable omega n. So it'd be I omega n squared, but I squared gives you minus sign. So it will be minus omega n plus omega n. So the transfer function will collapse into 0. So basically it means that your transfer function will produce no output. This is the effect of cancellation. So the system itself will cancel this type of signal. Okay. This is interesting, but not very typical in practice. But let us finally see what is extremely interesting in practice. And that is, if we pass it through this transfer function, which is a transfer function from the input to the output. So input, typical input, right, that drives us like external torque or something like this, external current, external voltage. If we pass it through this system, what happens is, again, here it will be J times frequency variable squared, all squared. Also I times frequency variable, all squared. I squared will give you a minus sign. So there will be a minus sign here. If we pass omega n through it, we will have minus omega n squared plus omega n squared. So it will be 0 in the denominator. So what will happen is the transfer function will become 1 over 0. So it will tend to infinity. So the Bode plot that you're going to plot here would have like a response going to infinity. Yeah, Bode is normally defined for stable systems. This is like marginally stable. So it's dubious to write Bode for it. But this is for amplitude response. We could plot amplitude response without Bode. For amplitude response, it is a classic. This is called resonance. Okay? This is called resonance. So as omega of the input signal approaches your natural frequency, you would have a resonance. And for this particular system, without damping, it means that your amplitude response is infinite. Your system will gain energy infinitely, like more and more and more, with no bounds. Normally, there is a bound for how much energy you would store from your signal. Here, there is no bounds. That is the famous example which we love to give is like a bridge collapsing under people marching through it, right? You have people who caught natural frequency with the marching, like they march periodically with the same kind of like frequency. The bridge gains and gains and gains and it's like energy, right? And eventually it collapses. So a classical example, like there is a whole body of comments that can be made about how realistic the scenarios are. But things like this happen. Natural frequency happen. You can see videos of bridges going up and down under unfortunate external input. And this is what we call resonance. And now you can see where resonance comes from. So resonance comes from considering eigenvalues of a system with 0 damping, which is like looks like this, or like this if you want. You can then reduce the solution for the system, which is you can just directly plug it in. You can consider transfer functions for the system, and you would find that transfer function near the natural frequency explodes. The natural frequency, if you are uncomfortable with using these variables, can always be found like this, just square root of your stiffness variable, right? Okay, we are completely out of time, but that was the last, almost the last slide. So this maybe we'll just discuss it on the next lecture if we have to. All right, so this is it. Now you have seen all of it until resonance. Good luck with your practical sessions. See you later, guys.